Thank you very much. Let me start by thanking the organizers for planning such a kind of innovative workshop, bringing people from a wide variety of streams into one place. So I wanted to talk a bit about how to constrain the nature of dark matter using neutral hydrogen in the universe. I understand the audience is quite mixed here, so if you find something is not clear, please feel free to ask me anytime. So what I plan to do is I will try to kind of motivate the discussion by talking about how people are thinking of constraining the nature of dark matter using small scale fluctuations in the cosmological density field. I will connect that to neutral hydrogen in the next part. And then I will talk about two kind of observations which are related to neutral hydrogen, which may help in constraining the dark matter. One is the Lyman-alpha forest. Other one are the 21-centimeter experiments. So this is something which we all know. We have about 27% of the energy budget dominated by something which is gravitating but showing no light. So we call it dark matter, and it's most likely non-baryonic. Now, one way of really, I mean, the one kind of probe which has told a lot about dark matter are the inhomogeneities in the universe. Basically, you see this big universe around us. It's not smooth. There are a lot of structures. And two examples are the CMB, which shows structures, but of tiny amplitude. Okay, 1 part in 10 to the 5 or so, probably 1 part in 10 to the 3 in the dark matter. And then closer to today, when we look at the, let's say, the galaxy surveys around us, we again see a lot of structure. The point is that these structures, in principle, tell us that dark matter is there and what kind of properties it should have to actually match some of the observational details. And one of them is what is known as the power spectrum. So what has been shown here is the power spectrum of matter fluctuations versus the wave number. So what you do is basically you take the underlying fluctuating matter density field, you Fourier transform it, you get something as a function of conjugate variable k, and basically the power spectrum is mod square of that. So that basically tells you how much power you have in the fluctuations at different scales. Remember, k is something which is inverse of the length scale. So small k means large scales and vice versa. And this plot made by the Planck collaboration shows basically kind of the data points inferred from various observations, and then they have just plotted in this. For example, the constraints on power spectrum at very large scales come from CMB. So these points are coming from various Planck measurements. And then you go to various galaxy surveys, including lensing. And at the smallest scale, the measurements come from what is known as the Lyman-alpha forest. And this is the kind of best fit ΛCDM power spectrum one has. And the claim is that it fits the data over a wide range of scales. And that basically is one pillar of ΛCDM. And I mean, just to understand, I mean, why, I mean, how this kind of in principle can constrain dark matter. For example, if the dark matter instead of being cold was hot, let's say neutrinos, I mean, almost massless neutrinos, what would have happened is you would have seen a strong suppression in the fluctuations at small scales. So this is, of course, a kind of cartoon which I have tried to draw. One can do much more sophisticated and quantitative analysis. But the fact that we don't see this suppression, I mean, helps us in ruling out, for example, hot dark matter as a dark matter candidate. So this kind of observations would tell you the fact that we don't see sufficient suppression is that dark matter needs to be kind of cold, okay? So non-relativistic, heavy, so on. But then there are, I mean, so, but it's also true that these data points have a lot of astrophysics in it. Interpreting them is not easy. There are large error bars. So you can ask a question, okay, fine, hot dark matter may be ruled out, but can I have something between cold and hot, let's say something like a warm dark matter, which can kind of account for these data points? Or how kind of hot or warm can we go? And this is where, I mean, a lot of activity is going on. Basically, people are looking for warm dark matter models, where what is shown here is the same power spectrum. It's just I have taken the earlier power spectrum and multiplied by k cube so that the shape is slightly different. But what you can see is what I have plotted here are theoretical expectation from the conventional CDM, and for two kind of warm dark matter models where the dark matter particle has a mass 1 keV and 2 keV, and you can see depending on the mass there is strong suppression in the power at small scales. So the question is, can we detect this suppression or can we rule out this suppression using observations? Now it's not very easy to do using CMB or galaxy surveys because they can take you up to scales somewhere around here. These scales are kind of very well probed by Lyman-alpha forest, and in the last decade or so a lot of activity was spent in trying to kind of constrain this part. Before going ahead, I should also say is that although I will be kind of always talking about warm dark matter and giving you numbers in terms of warm dark matter particles, I mean, any dark matter candidate which leads to suppression of power at small scales, in principle, any such candidate can be kind of studied using whatever I'm going to talk about in the rest of the talk. So warm dark matter is something which is very commonly used. I will be using that, but as I said, anything which affects the power spectrum at small scales can be studied using the observations which I'm going to discuss. So, yeah. Yes.
So where does scales that are showing on the right side?
Yes.
How do they compare to anything on the left?
They don't. Yes, these are large scales. These are intermediate scales. Sure.
So any scale you take here is completely subsumed in a dot.
Correct. Exactly. Yes.
So for this, you were just talking about the last.
Yes.
What are those sizes on that?
Those sizes will of course be, I mean, here we are talking about somewhere around roughly megaparsec or smaller scales. Okay, so yeah, these will be, I don't know, maybe intergalactic distance or something like that. But Lyman-alpha forest brings, I mean, it's a very different kind of probe, which let me just, once we come to that, I will see. So it really helps us in probing small scales. See, the problem in probing small scales with structure formation is that small scales things become extremely nonlinear, and that's the problem. Lyman-alpha forest is something which allows you to probe small scales without really going into nonlinear physics. So maybe I can talk about it offline, but that's where it really helps. So coming to Lyman-alpha forest and the theme of this talk, let's take a look at what is neutral hydrogen doing in our universe, because at the end I'm going to try to constrain dark matter or warm dark matter masses using neutral hydrogen. So neutral hydrogen formed for the first time in the what we call the last scattering epoch, and that's the epoch basically when the CMB originates. After that, the universe, the hydrogen is basically neutral throughout. I mean, there's hardly any ionized hydrogen. And that phase is known as the dark ages because there are no galaxies or stars in the universe present. At some point, we don't know exactly when, probably around redshifts of 30, maybe 20, the first stars in the universe form, and that's known as cosmic dawn. So that's the fancy name. So after dark ages, you enter the cosmic dawn. And once the stars form, the radiation coming out of the stars starts to affect the neutral hydrogen in several ways. And one way is that it completely ionizes the neutral hydrogen. If, for example, the stars have photons above the ionization potential of. So you end up in a very complicated process where there are regions around galaxies where hydrogen gets ionized, so it gets devoid of neutral hydrogen. And then these kind of what we call ionized bubbles which grow, overlap, and slowly the universe becomes completely ionized. And that probably happens somewhere around 5.5 to 6. And then we are living in a universe which we call the post-reionization universe, where actually bulk of the hydrogen is completely ionized. Whatever neutral hydrogen is present are present in like dense structures like galaxies inside that. So this is a story which I told you, but several aspects of this story has kind of already been established by different experiments. So, but although the lot of details are still to be worked out. Before going ahead, I mean, let's quickly also talk about the second most abundant element. So hydrogen, if hydrogen is the most abundant element, why leave out helium? So what happens to helium is that the first electron of helium gets ionized along with hydrogen, because the ionization potential of the first electron is very close to the hydrogen ionization potential. However, the second electron has a much higher ionization potential, 4 times that of hydrogen. So stars cannot produce such photons to ionize, to knock out the second electron of helium. You have to wait till something called quasars come up in a universe. Quasars are very energetic sources which can give out photons which can do the second ionization of helium. So second ionization of helium happens somewhere around redshifts 3 to 5. So there is this hydrogen ionization which happens from cosmic dawn to the epoch of reionization. We are talking about redshifts 20 to around redshifts of 5, 5.5 or 6. There is a helium reionization which happens somewhere around redshifts 3 to 5. That's our understanding. Now let's come to different probes of looking at neutral hydrogen. Let's talk about, let's go in the reverse direction. Let's talk about the post-reionization universe first. In a post-reionization universe where there are hardly any neutral hydrogen, whatever neutral hydrogen you have in the vast intergalactic space between galaxies are best probed by Lyman-alpha absorption. So what happens is there is a distant quasar, light is coming from the quasar to us, and that light, when it interacts with neutral hydrogen, gets absorbed because of Lyman-alpha transition, and it gives rise to this forest-like absorption structure in the spectra. So this is basically, you have to think about it as some kind of intensity versus wavelength, and all these structures are happening due to neutral hydrogen between the quasar and us. And basically, so this is just another way of showing it. And observed intensity is basically given by the unobserved intensity times exponential negative of a optical depth, and that optical depth is proportional to neutral hydrogen. It's also proportional to the cross section of Lyman-alpha absorption. Now this neutral hydrogen, I mean, in fact, if you work out these numbers, it will tell you that this neutral hydrogen is actually much smaller in number. The neutral hydrogen fraction is 1 part in 10 to the 5 probably. That is how we know that reionization occurred in the first place. But the crucial thing is this neutral hydrogen density traces the underlying dark matter density field. So basically the idea is, if we can study the fluctuations in this Lyman-alpha forest, we can understand the dark matter fluctuations as well, and hence calculate the power spectrum and then see whether we can understand a bit about warm dark matter. However, remember, this Lyman-alpha forest has a lot of astrophysics as well. For example, you need to know the underlying temperature field, you need to know how much ionizing radiation is present in that epoch, and so on. Okay. However, the advantage of Lyman-alpha forest is Lyman-alpha forest can be modeled using linear or most of the time quasi-linear theory, or simulations which require much less resources as compared to what you need for studying, for example, galaxies. Now, let's look at the Lyman-alpha power spectrum. So this is from a paper by a group done in 2017. So this is basically the power spectrum versus K. K is now in a different kind of unit. It's in inverse of velocity, but don't worry, it's still the qualitative is still the same. So these are basically large scales, these are small scales. So what has been plotted here are the power spectrum at different redshifts for different warm dark matter masses. Even without going into details, what you can see is that the warm dark matter starts to affect the power spectrum at these scales, which are basically very small scales. So if one can probe these small scales using the data, one can start to rule out the warm dark, one can start to constrain the warm dark matter mass, or probably rule out some warm dark matter models. So this is the basic idea. However, the story doesn't end here. For example, what happens if I change the temperature of that intergalactic medium which is hosting the neutral hydrogen. Again, the problem is it depends on the redshift, but at different redshifts, you can see the temperature also starts affecting the same small scales which you would have wanted to use to constrain the warm dark matter. Now that is what the problem is. So now unless you have a way to kind of measure the temperature, you won't be, I mean, the constraints on the warm dark matter won't be that strong. And it's not very easy to measure the temperature kind of independent, because you have to measure the temperature, you have to model the Lyman-alpha forest. To model the Lyman-alpha forest, you have to assume a cosmological model, in particular what kind of fluctuations you have to begin with. So it's completely degenerate in that sense. And as a result, whenever people try to put constraints on warm dark matter using Lyman-alpha forest, it really depended on how they modeled the temperature. So for example, this is another paper which came around 2019. And I mean, my point is to just show is, I mean, these are basically the warm dark matter mass constraints. And the constraints essentially depend, I mean, different lines are for different assumptions of the temperature field. And it really depends on what you do assume for temperature. So if you assume something very stringent for the temperature, you will get strong constraints. However, if you don't, the constraints will relax. Typically, I mean, at least this kind of work tends to give constraints where warm dark matter mass will be above somewhere around 2.5, 3 kilo electron volts. The problem is, why I'm harping on the temperature is that complication comes because of helium reionization. Remember, the redshifts one is trying to use to constrain the warm dark matter is somewhere between 4 to 5. And that is precisely where helium reionization starts to occur. Helium reionization leads to increase in the temperature of the intergalactic medium. And what then happens is the intergalactic medium becomes two-phase. There are places where helium is doubly ionized, so that place is heated up. There are places where helium is still singly ionized because the quasar radiation may not have reached there. So that is still cold. So what has been shown here is basically temperature as a function of density. But what you can show, what you can see is there are kind of two tracks depending on which phase of the intergalactic medium we are tracking. And as more and more helium gets reionized, this upper track starts to become populated. But what I'm trying to say is that the temperature of the intergalactic medium can be quite complicated around redshifts 3 to 4. And none of the simulations which try to constrain warm dark matter do account for this inhomogeneities in the temperature properly, the fact that you will have heated bubbles sitting around. So what we have decided to do is to take a couple of steps back and try to understand helium reionization first, and that's something which we are trying to do now. And hopefully once we understand helium reionization, that will help us in going back and trying to constrain warm dark matter. Now when we reach there, we don't know, but this is the approach we have been taking, which is complementary to some other groups. Now, this is our Lyman-alpha forest. What else can we do? Now, what happens is the other very crucial thing about dark matter is that they form halos. And these dark matter halos are essentially the places where eventually galaxies would form. So for example, in simulations, if you're talking about dark matter particles, I mean, they get bunched together in a group and they are classified as like collapsed. I mean, they decouple from the expansion of the universe and have these halos. And they will be identified by some group finding algorithms. And these halos are important because eventually the baryons or the gas will basically be attracted by the potential of these huge dark matter halos and eventually will undergo various reactions to form stars. I mean, I'm sure you've heard about halos in the previous week. Now, what has been shown here is what is known as the mass function. So number of halos per unit volume per unit mass versus mass for different redshifts. And you see, I mean, there are various features. So typically the halo mass function is dominated by small mass halos and it drops significantly at high mass. Also that at high redshift, the number of halos is small, and not only that, the number of the fraction of mass in high mass halos tend to become smaller at high redshift.
These are simulations of warm dark matter?
No, these are just cold dark matter simulations. Now, what happens if you do warm dark matter simulations? And this is basically based on simulations and fitting functions on that. So this is again the number of halos versus halo mass. This would be a typical CDM prediction. For warm dark matter, you will see suppression in this halo mass function again at small halo masses. So just like the small scale power spectrum or the small scale fluctuations get washed out, similarly, all the small mass halos also get suppressed. Their abundance gets suppressed. So now the question is, can we use this to understand warm dark matter? And hopefully that can be a probe complementary to what we do in the Lyman-alpha forest. In Lyman-alpha forest, we didn't have to worry about halos. That was one advantage, but then, yeah, there are always scope of warm dark matter, using halos. What happens is, yeah.
The difference between this plot and the plot of the power spectrum is that after the linear power spectrum, you have collapsed the objects into halos. So that's
yes.
reflected in this power spectrum.
Yes. This accounts for, yes, the halos are really nonlinear structures. So they have decoupled from the.
So that's the difference between this plot and the earlier plot of the power spectrum.
Yes, yeah. So power spectrum is the, yeah, it's actually large scale density field. Yeah, you are just catching the fluctuations there. You can probe those fluctuations using galaxies and halos also, but yeah, that was really at much larger scale. That's true. And there we are talking about individual objects and counting their numbers. So the question is, okay, fine. So why can't we go to some high redshift and, for example, look at the number of galaxies, and suppose we see a suppression in the number of galaxies at the faint end. So can we understand something about warm dark matter there? So this is something many people have tried to do, including us. So this is, for example, what we call the galaxy luminosity function. So this is the number of galaxies as a function of their luminosity at different redshifts and for different kind of warm dark matter models. And you can see, so fine, I mean, so the black one is the cold dark matter, and as you decrease the mass, you see the suppression. Now, two things which you have to worry about. Firstly, the data, which is shown with points with error bars, are still mostly at kind of at the level where it hasn't reached these kind of luminosities so as to allow us to distinguish between different dark matter models. So that's the first point to take. Hopefully with JWST things will become a bit better. The claim is they will detect more galaxies in the faint end as well. However, there are a lot of astrophysical effects happening, in particular something called feedback, which also suppresses, in principle can suppress the star formation in galaxies at faint end. So for example, I mean, there are models with different feedbacks also shown here. So that is another problem. So you just cannot go count the number of galaxies and try to constrain warm dark matter mass, because there are a lot of astrophysical effects which you have to account for. Solid and the dashed line are two different feedback mechanisms. Okay, so these are all semi kind of analytical kind of models where there are things which are kind of put using equations or sometimes by hand, but this is just to check. And you can see, I mean, yeah, so the feedback can also make a lot of difference. Now, that is where probably neutral hydrogen can again come to the rescue. So for example, we talked about one transition of neutral hydrogen, that was Lyman-alpha. Now, that was the electronic transition going from ground state to the first excited state. There is another transition which is very useful in astrophysics, that's the 21 centimeter, and that's happening because of the spin flip in the ground state of neutral hydrogen. And in this case, the frequencies we are talking about are 21 centimeter or something like 1.4 gigahertz. And these are basically very well studied using low frequency radio telescopes. In fact, currently, I mean, globally, there is a lot of effort going on to basically trying to detect this 21 centimeter signal. That is irrespective of whether you want to use that for dark matter or not. So for example, if you think of the 21 centimeter signal, you can try to detect its global average. So this will be, I mean, if you think in terms of CMB, this will be trying to detect just the black body part of the CMB without worrying about the spatial fluctuations. And there, I mean, there is again, depending on whether you want to do cosmic dawn or reionization, that will determine the frequency you are after. And this is not at all an exhaustive list. I mean, I've just picked up a few interesting experiments which are ongoing or coming up. Sarastri is something which is led by RRI in Bangalore. So, and edges which had become quite famous recently. I will probably talk about these in the next few minutes. And you can also try to do fluctuations. So these are basically trying to detect the 21 centimeter signal, but using spatial fluctuations. And in that case, for global signal, a small kind of element is fine. I mean, these telescopes are very small. However, to do the fluctuations, you need arrays of telescope, and there are a lot of such arrays operating. So MWI is in Australia, LOFAR in Netherlands and Europe, GMRT in India. This is basically built and kind of maintained by the institute I work in CRA. So this is very close to Pune. Chime in Canada, Meerkat in South Africa, and there are others as well. And the basic idea is CMB photons will be coming from the last scattering surface to us. In between, they may encounter H1, and depending on the state of the H1, either the CMB photons can get absorbed or the H1 can add some extra photons to this. So you may receive photons in excess or in less than what you expect from the standard CMB black body curve, and that's something one is planning to detect. How much different we have, the flux is how different the flux is compared to what we expect from CMB. And the signal is essentially, this signal will be proportional to the amount of neutral hydrogen you have, and how different is what we call the spin temperature, and that's basically the measure of the level population of this hyperfine states. How different these level population, the temperature characterizing this level population compared to the CMB. So that's the basic idea. And there is a lot of physics which determines these level populations and hence the spin temperature, and I won't go into that. But if you look at the typical reionization and cosmic dawn model and look at the global signal, so what has been plotted here is that the difference as compared to CMB. So 0 would be basically CMB here versus redshift or frequency. And I mean, this signal shows lot of features, and each of them has nice physics around it. But one feature which is very prominent, where there is absorption happening, and that happens exactly when the first galaxies form. Okay, so this is the state when the first galaxies form, this gets absorbed and then heating begins, it goes up. So and this is basically the cosmic dawn phase of the universe. So one hopes to detect this absorption using these 21 centimeter experiments. In fact, there was a claim of this detection using the experiment called edges. So they detected the signal, but it's not clear whether that signal is real or not. Firstly, the amplitude of the signal is much larger than what we expect from conventional reionization models. So if the signal is true, then probably something exotic is going on at those redshifts. But more importantly, I mean, people have also shown that this signal can be a result of systematics in the instrument. And later on, basically, a different experiment, which is the SARAS, run by RRI, when they tried to go and look at the same frequency range, they did not find any evidence of the signal. So in fact, they rule out this signal at some confidence level. So there is a controversy, but when the signal came up, we actually tried to model it. Now here the idea was very simple, that if these early galaxies, if the small mass halos are suppressed in the warm dark matter models, what will happen is formation of galaxies will get delayed. Why? Because the way we understand structure formation, it is hierarchical. Small halos form first, then they merge and form large halos. Now suppose there is a model where you cut off all the small mass halos, what will happen is they won't form. So you have to wait till the large mass halos form, and large mass halos form later. So as a result, the formation of the first galaxies will get delayed. So our idea was to see if there are kind of warm dark matter models where you cannot even form these first galaxies at the redshift at which the signal showed up. So with CDM, of course, I mean, we varied a lot of astrophysical parameters in the wide range, and one can see that there is a range of models which are probably okay with the signal. The signal is here. Yeah. But the moment you come to something like 3 keV dark matter models, it becomes very difficult to predict this signal, even accounting for the astrophysical uncertainties to the level we could account for in the model which we were dealing with. So at that point, we said that it's possible to rule out warm dark matter model less than 3 keV with ages data. But now that the data is gone, so this result itself is a bit, yeah, I mean, it is not very easy to kind of motivate this result anymore. As I said earlier, that ages signal could be spurious. And there was the other problem that the analysis which we did, it had a lot of galaxy formation physics put in, but we did not vary the cosmological parameters. And remember, these fluctuations, there is cosmology there as well, all this amplitude of the cosmological fluctuations, the power law slope and things like that. So in principle, one should vary those simultaneously. So we took a different approach where, I mean, we now have this called Cosmo-RIA and MC. So this is useful even without worrying about dark matter. It's basically a physically motivated analytical model of reionization and thermal history of the universe. So it's fast, it can run very quickly. It has coupled with the calculations of the CMB angular power spectra, and it's coupled also to a MCMC module. So what you can do is you can vary all the cosmological parameters as well as parameters which you require to model reionization and cosmic dawn basically. And basically it's a Python code which is extremely easy to use. And the other thing we did is we gave up on edges data, and we said that what will happen once future 21 centimeter data comes. So we generated mock 21 centimeter data for future experiments. Now suppose we want to constrain warm dark matter. To generate mock data, we have to assume something for the dark matter mass. So we assume two models here. One is that the dark matter is indeed cold dark matter. So you can take its mass to be kind of infinity for all practical purposes. And another one is hypothetical that warm dark matter mass is 7 keV. We just chose 7 keV. You could have chosen something else. And then we generated the mock data. We run our machinery. So you can see we varied all the parameters. These are some of the cosmological parameters. Here are some reionization parameters, and including the warm dark matter mass. And these are basically the forecasts we have on warm dark matter mass. So I mean, so the current best constraints we have, which is with existing data without worrying about 21 centimeter data, is the red one, which is quite weak. But remember, the x-axis is inverse of the warm dark matter mass. So this is basically infinite cold dark matter. This is light basically. So essentially what we are finding is that if the dark matter is indeed cold, then we should be, with these experiments, we should be ruled out at the level where warm dark matter can be something like greater than 7 keV or so. So this tells you the kind of power of this 21 centimeter experiments. If it is indeed 7 keV, then we should be able to detect. Okay, I mean, we should be able to rule out small or larger masses. So the 2 sigma, it will be between 5 and 10 keV. The higher confidence level, well, one can also. So basically, that's the idea. So this gives you an idea how different aspects of neutral hydrogen, one is Lyman-alpha, another one is 21 centimeter, can really help us in constraining warm dark matter mass. But as I said earlier also, you can generalize this to any dark matter models which affects the small scale fluctuations of the matter distribution. And people are doing it. I mean, people now often don't commit themselves to a particular model of dark matter, but take much more generic functions of suppression and try to constrain their parameters. So basically, the thing I wanted to convey is that in principle, the nature of dark matter can be constrained by their effect on small scale matter fluctuations. And one way to probe that is to use neutral hydrogen. One probe is the Lyman-alpha forest, and another one is the 21 centimeter plus CMB. So Lyman-alpha forest will probe the neutral hydrogen after reionization, and these ones will probe at much earlier redshifts. Now, I mean, both come with their own difficulties and problems. For example, Lyman-alpha forest constraints would require require us to know the temperature evolution, and for that we may need to know a bit about helium reionization. First stars, on the other hand, can provide complementary constraints, but there also modeling is a challenge, and we need, of course, we need data at high redshifts, which we still don't have. So let me stop here, and there's time for questions. I can take them.
Thank you, Tirthankar, for that very clear and comprehensive talk. So we can take some questions now.
Yes. Yeah. So there is an assumption there that at least it is not decaying to a substantial level. So the omega matter which you have, let us say the CMB where initial conditions for the simulations are set, is roughly remains the same throughout. Now, yeah, if it decays substantially, it will affect not only our analysis but various other. There is this other aspect, since I talked about neutral hydrogen, if it starts to decay into energetic photons, then it also starts to affect some of the conclusions regarding reionization I talked about. So it may be very interesting to actually do it simultaneously to see what happens. One, what happens to the small scale fluctuations, and for the same model, what happens to reionization. Reionization brings its own observational constraints, so it's not very easy to just do whatever you want kind of thing. So you may get strong constraints, provided you have a model to tell how it decays.
Can you tell briefly what sets the error bars on the measurements of one of the plots that you showed?
These ones?
Simon,
This one?
no. So okay, so
Lyman-alpha forest?
yeah, right. So my question is like, how much are we limited by the current observations, given that there are degeneracies in temperature and
these error bars, you mean? These error bars are set by, mostly the noise in the Lyman-alpha forest spectra. So that depends on how high quality observations you have. Second, it also, you need to actually go to reasonably high resolution spectra so as to probe small scales, and getting high signal to noise high resolution spectra is a challenge. And third is, you need to, if you have lot of quasars, which means large number of lines of sight, these error bars will decrease. So these are the main things which determine the error bar.
Can I ask one more? Okay. Yeah. So, so like you said, galaxies reside in dark matter halos, so you can model their occupation on these things. But
Yes.
how do you associate this the number density of these H1, whatever you measure, with the dark matter?
Yeah, you mean how? Okay, so there are two parts. One is how do you so there is this halos, and galaxies or stars will form there. How do we associate stars with dark matter halos is a very good question. So you need to understand a bit about star formation there. Our understanding of star formation at high redshift may be incomplete, and that essentially gives rise to, if you look at some of these plots, is a wide range of models. These are different kind of star formation models, whatever we could do, whatever is unknown in those cases. So it's quite a bit of things which are unknown, and that's something which we have to live. H1 is in the intergalactic space, so that roughly traces the linear dark matter. So that is easier to deal.
Okay, we'll take one last question.
Okay, so my doubt is regarding the Lyman-alpha signal that you get. So the way that you get a Lyman-alpha signal seems to be very streamlined, in the sense that you have to have a quasar that should go through a neutral hydrogen pocket and then reach the observer. So my question is, how statistically significant is the distribution of these neutral hydrogen pockets that you would expect to see the signal?
Yeah. So this neutral hydrogen is all over the space. So remember, this neutral hydrogen is residing not inside the galaxies, but in the intergalactic space. So this is basically neutral hydrogen which is tracing what we call this cosmic wave, Even voids will have a small amount of neutral hydrogen. This signal is produced by an extremely small amount of neutral hydrogen because Lyman-alpha is such a strong transition. Even 1 part in 10 to the 5 neutral atoms will give rise to this signal. So no matter in which directions you shoot a line of sight, there will be enough neutral hydrogen to see these structures. So we just need quasars. So if there is a quasar, there will be Lyman-alpha forest. So that's not a problem. Quasar at high redshift, there will be Lyman-alpha.
Okay, thank you.
In fact, with upcoming very sensitive telescopes, people are thinking of doing this with galaxies. Then you will have a larger number of lines of sights. And that will also show Lyman-alpha forest in principle. Now we cannot see because it's much fainter than the quasar.
Thank you.
Thank you, Tirthankar.